Okay. Hey, question one. We have to draw these two forces. I mean, like I said, it already gave you was the one. Um, the important thing about the forces is you know what direction they are. And any, especially when the forces are in the same plane, like I mean, they're both vertical. So that means the net force will be in one of those directions, okay? We want the rocket to move up, so that must be the direction of the net force. Secondly, for the net force to be up, then that means this thrust force must be longer. And so it is important you sketch that longer. Okay? All right. Wow, there's only one mark for that? Yeah, whatever. Okay, so the initial acceleration of the rocket is 15 meters per second. Calculate the thrust force of its engine at launch. Wow. We did talk about this. We did talk about how a net force, another way to say that is the sum of all forces. So the only forces we have is the thrust. I'm just going to write T here because I don't want to spell thrust. And then it's going to be plus Fg, but we'll see that Fg is one of these is going to be, I'm going to make it positive, so up, I'm going to say it's positive. So what's going to happen is that this net force, we don't have a net force yet, do we? But we do have an acceleration. Okay, that's good. And we know that when we have something like the mass and acceleration have a relationship with net force, right? So we just rearrange this. Net force equals mass times acceleration. So our mass is 1.5. Our acceleration is 15. Wow. The answer to this, I don't know if you guys know 15 times 15, but it's 225, so this is 2.25 newtons. Amazing. So there it is. Using that, we can fill this in now. What is the thrust? Well, the thrust, well, we'll just put these in because remember we added this. So what we're really doing is we're subtracting this negative, and mg, that Fg is mass times gravity, right? The wave force is mass times the acceleration of gravity, which is 9.8, not 10, please. And then that equals our net force over here. Okay, so this minus this equals the net force. So that means our thrust force will be bigger because when we move this negative over to this side, it will be bigger. Okay, so there it is, 225. This one, I'm not so good about doing it in my head, so I'll just get my calculator. There it is. What is it? Okay, we had 14.7. That's a 4. And we see that this is going to be 16 point, well, it's going to be more than 16.2. It's going to be 17, I think. Yeah, 17. Okay. So by the time we round this 9, it'll make it 17. Yay. And we have 3 significant figures. Yay. There it is. Okay. You can say it's up. Did I calculate this right? Oh, no, I didn't. My bad. It's 22.5. Double check your work, folks. Good thing I double checked this because it didn't make sense that this was so small. Okay, anyways. Yeah, it didn't make sense that, yeah, anyways. We'll add this together. This is going to be 37.2 now. Wow. Learn from my mistakes, please. Learn from my mistakes. and double check your work. Make sure you actually use the calculator. For 2 marks, all that for 2 marks. I don't think these older exams reflect the amount of work you have to do in a lot of the questions. So something like this is probably going to be more like 4 marks rather than 2 marks, okay? But that is a lot of work. Just understand, we can always find net force if we know the mass of something and its acceleration. And that net force is always the sum of any real forces acting on an object. So in this case, we have the thrust force and the weight force. Okay, any questions? It's 22.5. Yes, thank you. Thank you for that. Always somebody has to point out my mistakes. But thank you. You should. If I make a mistake on this, say something so everybody doesn't think what I'm saying is the truth. The acceleration of the velocity increases as it flies higher and higher. Suggest why this would happen. Well, what is acceleration? Well, the engine of the thrust stays the same, right? So, okay, that stays the same. Sure, but we are burning fuel, right? As it flies higher and higher. Sure, you could also argue that the gravity force is also reduced. That's true too. However, I think mainly you'll see that when the fuel is 60% of the weight or the mass, then as you're flying, you're burning fuel, right? So there it is. Fuel burned as rocket flies higher. Yeah. Acceleration, remember, is proportional to the inverse of mass. So less mass with the same amount of net force, okay, if we don't consider the gravity force reducing. So let's mean the same net force, then acceleration increases, okay? I'm not going to write everything, but here. There you go. And this is the evidence right here, this one. And based on this fact, of course, okay? So that's showing knowledge of how acceleration changes because of mass. Mr. Kuhlman, come on in. Okay, what's the next one? It wasn't this. I mean, we could come back to this later, but I believe it's number 7. Let me check my list. Number 7, yes. Number 7 is a wave. Definitely. Definitely a wave. In this case, it's a sound wave. Okay? This is really how the sound wave is, as you guys know. This is a longitudinal wave, but it can be represented in terms of its pressure. So this part, compression part, is high pressure, and this can be low pressure, this refraction part. So low pressure, high pressure. There you go. And you can see what they do is the sound waves moving through the air at 25 degrees Celsius may be important. Indicates the variation of, okay, anyways. Calculate the values of the quantities for this sound wave. Wavelength. We know that a wavelength is the distance from one part of the wave to exactly the same part of the wave. So this is the wavelength, okay? There's one wavelength. Or you could have gone, why do I choose that? Because the total length is based on the peak here and the peak here. So, there we go. You can draw this in if you wish. There are 4 wavelengths. So how do I find one wavelength? Well, the total length is that. And there are 4 wavelengths. So, 1 point. This time I'm confident in my calculations. It's not that. It's 5, isn't it? Not that confident. I'll just use a calculator. I think it's 1.56. Yeah, it is. There it is. It says meters. I'm going to write meters. Frequency. Well, frequency. Frequency, well, we don't have a time for how many of these wavelengths are seen, right? What we do are given is air. Sound moves at a certain velocity. The sound has a fixed velocity depending on the temperature. How do I know this? Because it's 25 degrees Celsius. The speed of air, sound in air, is this at 25 degrees Celsius, 346 meters per second. It is a constant. Of course, if the temperature changes, then the speed of air wave is, sound wave is different. But frequency is, according to the wave equation, wavelength times frequency. Wow. So there we go. Frequency is speed of sound, sound waves, divided by the wavelength. So there it is. It's going to be equal to 346 divided by the wavelength. Okay. And yeah, 346. Oh, oh, oh. 346 divided by the answer, the previous answer, obviously, and it gives us that. 221 rounded to 222, 222 hertz. Yeah. Okay. The period. Well, there is a relationship between this frequency and the period. Okay? Period, they have an inverse relationship. We know that inverse means 1 over that thing. So there it is. Period is the inverse of frequency. So it's 1 over 22. I can do this. Boop. See, this is the inverse of the answer. Is that it's going to be 4.51 times 10 to the 1, 2, 3, negative 3. So 4.51 times 10 to the negative 3 seconds. Wow. Amazing. Okay? Super duper easy stuff, I hope. Understanding waves. Yeah. Oh. Ooh. It's a close pipe. Okay, so we're getting to number 17. And it looks like the clarinet is a wind instrument that behaves like a closed pipe with a fundamental frequency. So we got F equals that. It says closed pipe. So I hope if you recall that if you have your student book, what do we know about, what's the difference between closed pipe and an open pipe? By the way, open pipe and fixed string are the same. Strings and open pipes are the same. Closed pipe is different. Sorry, I might, if I'm kind of sniffing a little bit because my nose is clogging in this air conditioner that's right behind me. Remember, these revisions are best when I get a two-way communication here. Like you talking to me talking to you. Pretend there's no one else here but you and me. Ignore those other 4 people. And anybody else who'll be watching this video later. Don't be shy. What is the difference between their harmonics? A little bit like that, sure. Sure. Okay, we'll just do a quick review of pipes. So, open, okay, if you guys recall, they have frequencies or harmonics, as Yi pointed out, in, yeah, so this is one of the fundamental frequencies. So the next harmonic for open is 2, double that frequency, and then 3, and then 4, and then so on and so on. So there's the first frequency harmonic, second, third, fourth, like that, just like that. And they have their own equation, okay, for closed and open pipe. So here it is, the relationship between the wavelength and the length of the pipe, okay, and whichever mode or harmonic you're in, you're looking for, okay, so there's that. Now, what's different? So the mode is like the next harmonic. So you saw in the open pipe that we have 1, 2, 3, 4. So you would put that in here for N, okay? So the first mode, first harmonic, second mode, second harmonic. The thing about closed pipes, though, is that they have only odd modes of harmonics, not modes, harmonics. Okay, so what happens is you get 1, the fundamental one, then you get 3, and then you get 5 times that, and then you get 7, and so on and so on. Okay, so they're the odd ones, there's no even ones. It has to do with how waves are formed inside the pipes. Okay, so there's the closed one. Why is it closed? One end's closed. And the way it's formed is that the fundamental frequency for a closed pipe is only 1/4 of a wave, okay? And it equals the length of the pipe. So that's why, and so if you had double the wavelength or double the frequency, right, you would only have, let's see what happens if we did double the wavelength, which would be double the frequency. See? So now this is half the wavelength, double the frequency. What happens is you got an antinode. You can't have an antinode at the opening because that makes no sound. That's why there are no even ones, only the odd ones. So now if I go 3 times that wavelength, which would be 3/4 wavelength, it's, as you can see now, it would go like this. Okay, so we would have node, node, and then should be another node for a full one, but you can see it's at antinode again, which is why we can hear the sound. Antinode, antinode, that's why we hear the sound. Okay? No means no sound. So that's why they're odd frequencies. Okay, and it has its own equation. So the difference between the two, you can see? So one wavelength one length of the pipe is half a wavelength for open pipes. And then one length for the fundamental frequency, the length of the pipe is 1/4. If you move this over, it'd be divided. So 1/4 of a wavelength, okay? And then the end is the mode. So that's it. You'll see, pretty easy, right? Pretty easy. Okay. Yeah, still sniffling. I'm sorry about that. It's annoying to hear. I know. Now you know how it is for everybody taking an exam when you're sniffling. Okay. Room temperature. Air is at room temperature, 25 degrees. You guys know what that means. That means the velocity of air is 3, 4, 6 meters per second. Remember? We just looked at that in the previous part. What are the frequencies of the next 2 higher harmonics? Okay, so this is closed, right? Nothing, we just talked about all this. So F we know is 130. The next two higher ones is 3F because it'll only be the odd one. So it's going to be 3 times 130. I don't think I need a calculator for this one, but who knows? I've shown you before. Sometimes I miss them. Okay, and this one is that exactly the same thing. F, 5 Fs. So 650 hertz. Okay, the frequencies. Boom, we good. Sketch the particle displacement versus the distance envelopes. I mean, is this just the pipe? This is the length of the pipe. Distance envelope. For the following frequency and for the next harmonic above the front in this one. Wow. So the next one above the fundamental frequency is the 3F. 3Fs. Okay. Again, you want to know how much? Well, you could use the formula. You don't really need it, but you could. Okay, so there it is. If we put that in here, wavelength equals 4L over 2, the first mode, I guess that's 1 minus 1. You know, that's 1 on the bottom. So you can see the length of the tube, L, is equal to the wavelength. 4 of those equal to wavelength. So really, the length is 1/4 of a wavelength. Sorry about the symbols. Let me just do that better. There we go. So one length of the pipe is just 1/4 of a wavelength for that frequency. There it is. Let's do it. 1/4 means choo. Remember, one wavelength, if we look at it as in terms of a standing wave, and we flex back, you can see the thing. There's half, and there's 1/4. You see, you go from the 0 position to the highest part of the amplitude. 0 positions to the highest part of the amplitude, and then we do the other part because there are standing waves. There you go. Okay? Now the next one. The next frequency, if I were to show that like this, 4L, the next mode is 2 times 2, right? It's the second mode, which is the third frequency. 3, so you can see that would be 3. This will be 3 in the bottom. 4 minus 1 is 3. Divided by 4. See, still that. So the length of the pipe fits 3/4 of a wavelength. 3/4 of a wavelength means here. So we're going to go up, and we should end up, as you can see, antinode. Okay? The antinode begins here. We should have a node here and there. 1/3 of the way, 1/2, 1/4. See? There it is. Ta-da! Yep. It makes sense. You just have 3/4 of a wave. So split this pipe length into thirds. 1, 2, 3. 2, 3. See? And then you draw it. That's it. Well done. Any questions? Calculate the length of the clarinet. Ooh. Well, depends which one you want to use. Shall we use the fundamental frequency because it's kind of the easiest one? We can use whichever one, but we'll use this one because the fundamental frequency is already given to us. We didn't calculate it. You can use the third harmonic too, but it doesn't matter. Okay, so what is the length of the pipe? Well, we know that we know that there's 1/4 of a wavelength for the fundamental frequency in that length of pipe. 1/4 of a wave. So why don't we find the length of a wave? How do we find that? From the information we already know, according to the question, We know that the air in the room is 25 degrees, so we know that the sound would move at 346 meters per second. We know its fundamental frequency is 130 hertz, and we know there's a relationship between those three things. The wave equation, V equals that times that. So this is going to be V divided by this. Wow. 346 divided by 130 hertz equals something. Not going to do it in my head. You know how that turns out. Disaster. 346 divided by 130. It's going to be 2 something. Ooh, it's 2.66 meters because that's the base, what do you call it, unit. Now, because we use the fundamental frequency, then that means the length of the pipe contains only 1/4 of a wavelength, right? So, what is the length? You use that equation if you wish, right, guys? But since it's only 1, right, length equals that. So we got 266 divided by 4, easy peasy, divided by 4. It's 0.665 meters. Okay? Again, it's us establishing that for that particular frequency, how much of the wave is inside. And the trick to this one is that for the open end, it's always has to be a, what do you call it? Antinode, like the open part, the highest point of the wave form. So what happens if it was an open, totally open, rather than like 2 open? Well, like we said, it can't be a node at the end. And there always has to be at least 1 node. It's the fundamental frequency, so it's 1 node. And there it is. It's actually half a wavelength. Peak to trough. Peak to trough is half a wavelength. And so there it is. There's your 2 nodes at the end, and there's that one antinodes. I'm sorry, at the end, and there's the 1 node for the fundamental frequency. There's the 1 node for the fundamental frequency. There's 2 for the next mode. See, 2 nodes, next mode. That's how it works. Okay. Any other questions? I feel like a comedian telling bad jokes. It is just dead in here. There's no laugh. There's nothing. No sound. Like a bad comedian. Okay. The clarinet is played. Why don't we take a break? We're gonna practice what we preach. We're gonna do studying. 30 minutes. Take a 5-minute break. You want to chat? You want to talk to somebody else? You want to just go offline? Whatever. But in 5 minutes, I'm gonna start back up. In the meantime, what's everybody doing? I'm not even gonna do that. I'm just gonna look away. I'm looking outside. It's super cloudy right now. We'll be back in 5 minutes. I'm just gonna pause the video now. No. I forgot. I didn't spell all of it, but did you know that? It's true. Yes, you got me. You got it. Cry me a river. Wait, did I spell 22 right? 22, correct. Okay, okay, it's a bad one, I know, but the bad ones are the good ones. We back now? That's 5 minutes. I think your brain has decompressed a bit. Okay, yeah, you gotta let it relax, you know, because you know when you use a muscle too much, you guys done seen this, PE, it swells up, it's all red, it pushes against your brain pushes against your head, and then suddenly, you know, you can't think, right, Kuman? Just can't think. Too much brain squeeze. Okay, let's get back to this. I have to unpause. Hold on a second. Okay, we're back. Hope you decompressed. The clarinet is played as to produce its fundamental frequency. The sound is captured by a microphone and fed into an amp. Two loudspeakers, X and Y, are connected in phase to the amplifier and set up facing each other at a distance of 8.5 meters apart. Thank you. I mean, it's already there. Person walking from one loudspeaker to the other towards the other hears points where the sound is extremely soft, alternating points where it is loud. Why will the person hear a series of soft and loud when they walk from one speaker to the other? Well, it did say that they're connected in phase, right? So you know the sound's going out like this. What happens is sometimes a crest and a crest meet, and sometimes the crest and the trough, the crest of this one and the trough of this one meet. And so, yeah, we get these lines of soft and loud, okay? Yeah, I mean, obviously my drawing's not great, but you get the picture. So what happens? These two waves, because it's a single frequency, so it's the same sound, so it's just the same wave emitting from these two speakers, one this way and one that way, and when they meet, sometimes, you know, they interfere. Okay? So as they walk, as the person walks, the speakers they interfere with each other, right? Interfere. The speakers' sounds, really the waves, sound waves, interfere with each other, creating loud, uh, okay, constructive interference, and that's the loud one, and destructive, sorry about the writing, interference. And that's the soft sound. And they alternate. They alternate. It just means that as you're walking, then you hear it soft, and then you hear it loud, and then you hear it soft, and you hear it loud, because of the fact that just like a wave, the wave is both high amplitude and low amplitude, and then sometimes they meet, the highs meet, and the lows meet together, or the low and a high meet together. Okay. Okay, so that's, you could also say the parts that are constructive are in phase, and the parts that are destructive interference are out of phase, right? That's when we got the trough meeting the crest. So I would say key points is that Yeah, constructive is loud part, in phase, and the destructive interference is the soft parts that are out of phase and they alternate. Okay, part E. Calculate whether the sound is loud or soft when the person walking beneath the speakers is 2.29 meters from speaker X. Okay, let's see. 2 point from X, right? So they're here. Just going to go out a quick diagram. Here they're 2.29 meters. And then how far are they away from the other speaker? Remember, the total length between them is 8.5 meters, right? So this side is going to be 8.5 minus this length. So this distance from that speaker is that. This distance is 8.5 minus 2.92. It's going to be 5.58. Well, what does that give us? Now, for this path length, there's that one, yes, and then there's this one, right? So what we want to do is, we know the path of this one is that sound coming this way and sound coming this way, and then we want to know the difference between those distances. Okay, so we got S1, we have S2. The sound has to travel that far before it meets this sound, and it's traveled that far. And by the time they meet, their wavelengths, depending on how far it is from the source, will meet the other wavelengths, and we don't know if it's a crest to crest or a trough to a crest to trough. So there's the soft sound, there'd be the high sound, okay, or the loud sound, I should say. So we got to find the difference between them. So we take the first distance, S2, which is 5.58, and we minus the second one, or the first one, whatever. Doesn't matter. Just take the bigger one and minus the smaller one. And we just want to know what difference in the sound waves, okay? So that means minus 2.92, not 29, plus 29.2, minus 2.29. There it is. Wow, look at that. It's 2.66. Does that look like anything else? Remember, this is played using the fundamental frequency of the clarinet. So let's go back. Oh, look at that. Look at that. The fundamental frequency's sound wave wavelength is 2.66 meters. So that means we have a difference of sound waves of exactly one wavelength of sound. So basically, do we hear a loud or a soft sound when the difference, you see the difference is equal to one wavelength? When we have a difference of a whole wavelength, it could be 2 wavelengths, 3 wavelengths, or in this case 1 wavelength, that means it's constructive interference. They're in phase. So what is the question asking again? Calculate whether the sound is okay. Therefore, it's loud. Difference in wavelength is a whole wavelength. So that means they're in phase. Okay? It just means that the one speaker might have shown one wave, and then the other one might have been 2 waves. One, oh, I should have drawn the other way. One, and so now by the time it meets the other one, it's exactly in phase with the, see? There's a difference. If this, where they met, this was 1 wavelength, and this was 1, this was 2, and this was 1, then that means they had a difference of 1. So they're in phase. Okay, that's it. We've done something like this before. Um, again, it depends on how far you're away from each sound source, and when the waves meet you, are they meeting over each other where the difference between their distances is equal to a whole wavelength, or is it equal to half wavelengths? So it could be 1.5, it could be 2.5 wavelengths difference. And what happens is that half tells you that a crest and a trough are meeting, and so that would be destructive interference, and you would hear a soft sound. So what is the difference between a soft and a loud point? Well, in a wave, you're basically saying a nodal, antinodal. What is the difference between nodes and antinodals, right? Okay. So we got node, antinode, node, antinode, node. So in a single wave, an antinode is when you get a higher amplitude, and a node is when there's zero amplitude. So you can see in a single wave, the difference between a node and an antinode is just 1/4 of a wave. Okay? This is so true. This is also true when we look at pipes. What separates the highest part, the trough, and the peaks, or the crests, from the zero line where the nodes are, okay? Because they show that there is no amplitude in either direction. So it's 1/4 of a wavelength. And in this case, it's 2.66 divided by 4, which happens to be the length of the previous question we did, okay? Right here, when it asked us what's the length of the pipe for a closed pipe, because that was 1/4 of a wavelength as well. Determine the number of soft points between the loudspeakers. Okay, well, if that means if we have a soft point, and then we have a loud point, right? And then we have a soft point. We know that the distance between the soft and loud point is 0.665. So that means the distance to the next one is 2 times that. 2 times that. So if I double this, it'd be 0.322.1, right? So 1.23 meters. I'm going to get rid of that 0. And so there is the distance between soft and soft. How many would we get? The midpoint would be, remember, the midpoint between any two speakers is always the loud point. So there's a loud one. And then that means there's only 4.25 meters here. And we know there's a difference. There's going to be one soft one here, which is 0.665 away. And as soon as you get that one, then you can divide the other ones. Okay, so we have 3.58 left. Okay, so the remaining distance we have is 3.58 meters left. And in that, well, what can we do? .58. So how many more soft ones can we get? So how many more soft ones can we get? We know that each soft one is 1.23 meters away from each other. I'm pretty sure if I go 1.23, I can probably do this at least 2 times, right? Right? So there's going to be another one and another one. So there's, how much would that be? 3.58 minus 1.23 minus 1.23. Oh, there's not another soft one in there, okay? There's not enough distance to get another soft one. So that's 1, 2, 3 on this side, And this side is going to be the same, so it's 1, 2, 3, a total of 6. It's kind of hard to show this in a good, nice way. There would be 6 soft points. There's really no easy way to show this, guys. The distance between each soft one is 1.23 meters, okay? You know that in the center, there's always a loud one because they're exactly in phase. They'll be in phase here. And we know that from the center, we get our first soft one, which is that far away. And so what that means is for the rest of this distance, we get this many remaining, right? So then from that, I just subtract another distance for a soft one, another distance for a soft one. And by the time I get to there, there's only 1.25. There's not enough for another soft one to occur. And so there's 3 on this side, and then there's 3 on that side. That's a total of 6. Yeah. Waves, super duper fun. Sorry, guys. It's what it is. It's what it is. Okay, we got time for number 18 before we get into our last bit, okay, or our next break. So I think we'll just do the first 3 for 18 because there's like a lot of parts to this one. All right, let's take a look at this. We have a car. Car has a mass. I'll just write it. If I have a diagram, I'll just write it there with the diagram so I don't lose the information. If I can look at this information, it's much quicker than me reading everything again. Okay? So please take the time. It's actually faster. Runs into the back of a stationary one. Okay, so this one's 0, u equals 0, and its mass is 3.5 tons, so that's 3,500 kilograms. Make it all the same. The car they lock together, okay, and slide to the halt in the middle. Skid marks. And they slide 3.2 meters. They estimate the friction on that was approximately the combined weight. Ooh, okay, wow. Okay, F, this is getting complicated. Okay, FG of them both, right? The weight, it says the weight, the combined weight. Okay, give a value for the force acting on the tires and skidder, and hence calculate the work done by the friction in bringing the vehicles to a stop. Okay, so work done refers to, we have given a distance, right? The skid marks, so we're given a distance here, S. So work is energy. Work energy is a force times a distance that the force was applied over, okay? So our force in this situation is the frictional force, and the frictional force is 60% of the weight force. So let's calculate that out. 0.6 times 9.8 times the combination of those two, which is 1,200 plus 3,200 times the weight force, right? So 9.8 times 4,400 times 60%. Whoops, that's not 60%. Okay, so it's 2,5,872. It's about that. All right, we don't have to round it yet. We can if we want to. So 2,5,872. You get marks for this, so show that, please. Times the distance it went. Okay, voila, 3.5. And then we gotta, round that to 3 significant figures. So 90600 joules, or 9.06 times 10 to the power of 4. is scientific notation. Ugh. Is that right? 3 point. Oh, oh, oh. That's not right. It's not 3.5. It's 3.2. Nobody said anything? Unbelievable. Unbelievable. 3. So it's going to be 8 to 8. Okay. 8 to 8. No one pointed that out? It's not 5, guys. It's 3, 2. Okay, that's it. There it is. The work done by the tires, by the friction on the tires, is because of the force of friction, which is 60% of the weight force. It said that. And over a distance of 3.2 meters. All right. State the energy transformation that occurs as the two skid to a halt. So it goes from energy transformation. Oh, okay. So what we're getting is that energy that these have, they're not like nuclear or electrical, right? They're moving. So what they have is they had kinetic energy when they were moving. But what happens to all that energy when they skid to a stop? I mean, you can see it in the movies. The tires smoke because they become heat. Okay, so it's taking the moving energy, the kinetic energy, and it's basically heat and a little bit of sound because you hear that too. So mainly heat. That's it. Hence, find the speed of the two vehicles immediately after the car runs into the van at the beginning of this. Ooh. Okay. Well, we just said it's kinetic energy it had, right? And it took this much energy to stop the vehicle, correct? Okay. So the work energy took to stop the vehicle was the energy it had in kinetic energy, right? And that kinetic energy is 1/2. You can find it in your formula sheet. When we go back up here, 1/2 mass velocity squared. How do I know that this is the situation? Because it talks about work energy, kinetic energy. It's the only information we have. We don't know any final velocity. We don't know any acceleration. You could possibly find that. There is a way to do that. But I think when you did acceleration due to the frictional force, it's just more work. It is more work. I'm going to say it is more work. So what do we have? 8 to 8. 8 to 8, 0, 0. There's half. We know the mass is for the mass of the car, right? Hence, find the immediately after the car runs. Hence, find the speed of the two vehicles immediately the car runs into the van. Okay, so that's their combination of their weight force. Oh my God, guys, look at the weight force. Mass is 35. Oh my God, you guys, let me do this. This is 35. That just totally changes all my answers. Okay, hold on. Let me just double check this. Plus 3,500. Okay, times 9.8 times 0.6. Alrighty then. Let's make sure we get all the right numbers now. Good thing this is math. It's kind of easy. It's just the understanding and getting, okay, thank goodness we're getting there. 8 4 0 0 8 4. Okay, that's what happened. I was looking at that and I didn't add it up right. So the mass of both of them, and just as they're about to hit v squared, so v equals the square root of this comes over here, so it's going to be 2 times that. It's another 0, right? Yeah. 1 2 3 4. Nope. 1. I have too many zeros there. Okay, so 2 times that, and then divided by that. Okay, that was. Please don't let me mess up anymore. Okay, 2 times 8 8 4 0 0. It's just calculations. Obviously, it's important when you're doing this, but I'm just kind of speed along here for you guys. So I got about 6.13 meters per second. Ta-da! Fantastic. Okay. So that was their speed. Their combined speed at that point. Given that momentum is conserved during the collision. Okay, so momentum. Determine the speed of the car before hitting the van. Okay, so P before equals P after. Well, we know what their velocity is just right after the collision. So, and we know their mass, so V1 is the same, okay? Mass, V2, mass 2, mass 1, so this will be 12. Because the velocities are the same, I don't need to add them together. Okay, there. That's the velocity is the same. We just take it out and then we'll multiply it to adding the two masses, which is 6.13, and then the mass of the car. I'll just write it up here. So the mass of the car is 12. We want to find its initial velocity plus 0, right? Because that's not moving, so it has no momentum. And so now we can solve for this momentum part. And so the initial velocity of the car equals this divided by 1200. So all that divided by the mass of the car equals u. Okay, so what do we got here? 4,700 for the mass of them combined times their velocity and divided by the mass of the car itself. And that'll give us the velocity of the car. 24.0 meters per second. And I like how it works out like that because you probably did it right when it comes out to a whole number like that. Okay, so that gets us to our second break because we gotta, decompress a bit. Any questions here? Anything I need to go say again? Which part you'd like me to talk about again? You understand the conservation of momentum? Momentum is based on a car's mass and its velocity. So we had the two cars. Before, in the first part, only the car was moving, so it's the only one with momentum. The van has 0 momentum because it's not moving, 0 velocity, 0. And then afterwards, after the collision, they're stuck together and they're moving at the same velocity. So that's why I make their velocity, and I take this velocity, and I take it out, and I take this one out. And when you do that, it's like you just multiplying by the velocity now. The two masses combined, okay? And then up here, energy is energy. So it was kinetic energy that was moving the car first, and that helped us to find the velocity of them. And that was it. Pretty much it. We used all the information. Okay. All right. I'm gonna take this little break now. So let's pause the video for a second. Okay. So again, before the collision, just the car had that velocity. We got it from the previous one. There's this total kinetic energy. And then the kinetic energy of them after is already given to us because we figured that out already. And you can see there's a big difference between the two. This is 345,000. This is only 88,000. So what happened to that account for any difference? Because the difference is because of the heat energy and sound. Remember the sound, I said something about sound and sound lost. That's why. Okay. These explanation ones, guys, you gotta still answer them best you can. But don't waste your time on them at first if you find them difficult. Stay them. Compare the force experienced by each vehicle during the collision. Explain why the car driver is likely to suffer injury as a result of the collision than the van driver. Okay? Well, according to Newton's third law, they both experience, both experience the same force. Because that's Newton's third law. If one exerts a force on an object, the object also exerts the same amount of force on the other. Okay? Why is the driver more likely to suffer? Well, according to Newton's second law, acceleration is a matter of the net force, which is the same for both of them, right? They both experience the same force. But because the mass here is smaller, the acceleration for the car is greater than the acceleration of the van. So that means the person inside experiences different accelerations, right? The car experiences a deceleration that's big because its mass is smaller. Let's compare the mass. The mass of the car is smaller than the mass of the van. And remember, they have an inverse relationship. So if the mass of the car is smaller than the van, then that means the acceleration the car experiences is greater than the van for the same amount of force that we established up here, okay? So that means the deceleration of the car driver is more than the acceleration of the van. So they get to the same velocity. Yes, sir. Nobody said it was easy. Any questions here? Nope. Bad comedian. I know. Okay. 20. Question 20 is anything to do with forces in different directions. If that's the case, then we have to draw vector diagrams, maybe. Yes, sir. Draw on the diagram. Okay, girl's riding down the hill. There's a 10-degree slope. Yes. The girl has a combined mass with her bike of 65 kilogram. There is a friction force. Okay. 15 newtons. Okay, mass is 65, yes. Okay. On the diagram, draw in and label the three forces acting on the girl and her bike as she starts rolling down the hill. Okay, great. Well, she's got a weight force. Yes. You can say weight. You can say FG. You can say whatever you like. This is the normal force, Fn, or you can say normal. You can say normal reaction. Please use a ruler and draw a straight line. That's not straight. And then friction force is going to be that way. Those are the three real ones. However, even though there's a friction force here, these two actually have a net force. Yeah. How large is the normal force of the road pushing on the tires? Okay. Well, you can see that best if we draw. Is she going to, it doesn't say if she is going at constant velocity or not. We won't know yet, okay? We don't know yet. So, there it is. There's the wave force. Oh, I draw it on the other side. I need to. And there is the normal force. Okay? And they will create a net force. That's their net force. I don't know what it is compared to the friction. I don't know, but I know that the angle goes here because it's opposite that net force that these two create. And so, because I know that this wave force is 65 kilograms times 9.8, then I know I can find the normal force quite easily. Okay. So this wave force is the hypotenuse, and this is the adjacent side. So cosine of the angle equals the normal force divided by the wave force. Okay, so Fn equals the wave force times cosine. I'm just rearranging that formula. Once I do that, just plug in my numbers. And I'll get something. $627 newtons. Bing! Okay. There's the normal force. Calculate the size of the net force on the girl as she starts rolling down the hill and her initial acceleration. So remember, we can only get friction force if she's moving. So just before she does that, what's her initial acceleration? Because that's to be the greatest then, because the net force will be greatest downwards at that point. And it's just this. We drew that vector diagram to help us. And so F net is going to be over W, and it's going to equal, that sine of the angle. I just did it backwards though. So F net equals W times sine of the angle, which we know now. We don't know. I never actually calculated it out. There it is. And then sine of 10%, or 10 degrees, I should say. And I'm just going to go up here and change this to sine, because why not? One newtons. And her initial acceleration. Okay, so but she's moving now, so she's got, that's not the net force. The real net force is this one, net, I don't even know how to say it, force down the slope. I'm going to change this because I don't want two net force along slope, so parallel to slope, and so the net force is going to be that force parallel to slope minus the friction force. Okay, so it's going to be 111 minus 15. Well, I don't know, 96 newtons. Okay. Are we done yet? No. It asks us, what is the initial acceleration? Okay, yes, F net divided by the mass. Yes, sir. Yes, sir. 3 bags full. Whew. There we go. 1.48 meters per second squared. Acceleration. Okay? So there it is again. I'll walk through it again. I want to find the force of the combined weight force and normal force. I should have just done I could have done Pythagoras theorem as well, you know. The square root of Fn squared plus F of W squared, okay? That's fine. But this way is fine. I found that amount of force, those two combined, and then to find the net force along the slope, I took that and minus the friction force, which is the opposite direction. Okay, so there is another one here. It's not a real one, so that's why we didn't draw it in. It's just the slope, the force along the slope due to these two. Okay, don't draw it in because that's not what the question asks you to do. And then once I found that net force, I was able to calculate the acceleration that net force has on the mass of the girl and the bike. In addition to the 15 newtons friction force, there is an air resistance force opposing her motion down the slope, which increases quadratically with speed according to the formula, blah, blah, blah. Okay. Calculate the maximum she will reach. Maximum she will reach rolling down the slope on her bike. Whew. Well, remember, the net force down right now is 96 newtons. We've already subtracted the friction force. So the air resistance has to equal that so that F net is 0 and that becomes constant velocity. Because as long as the net force is greater than the air resistance force, then you'll always get acceleration in this net force direction. So the only way that we get the maximum speed is when F net equals F air. See? So how do we know that? Well, there it is. We just put it in. See? Oh, it's 96, isn't it? Nobody's correcting me again? Come on, guys. Wake up. Wake up. So the only way that we get 0, everything equals 0, is those two equal each other. So that means 96. I'm going to use this formula. Equals 1.2 v squared. See, v equals the square root of 96 divided by 1.2. Okay. So what do we get from that? Square root. That. We get that. 8.94 meters per second. Boom. Hallelujah. We almost done. I'm on my last legs here. Okay. Yeah, we're almost there. Thanks for hanging in, troopers. We did have a request by another student. We're not going to name any names here because unless they want me to talk about them. It goes back to the 2011, I believe. Yeah, guys, some of these, yeah. That was question number 17. Is that right? Was it question number 17? Oh, cumin. Cumin, you gave yourself away. See, I set you up. I didn't think you would say anything, but okay, he gave himself away. Yeah, cumin was 17, wasn't it? Is it back here? Okay, so here it is, 17 is asking about these three radioactive particles, right? So these three radiations. Now it's saying it's going between parallel plates. You guys will learn about parallel plates and the electric field that's created between them next year. But we have these three particles. Gamma, not really a particle, but you know, whatever. They're going to go through here. So each one of these is going to get a chance to go through right through here, and then as they enter this part here, what's going to happen to them? Sketch the approximate paths that the alpha, beta, and gamma particles as they enter this electric field, showing the degree of curvature for each and clearly label each path. Okay, so we got to know a little something about these particles in terms of, well, this is a positive electrical charge and this is a negative. So, okay, so we know that alpha has, in terms of how many elementary charge it has, it's actually plus 2. 2 of those double the elementary charge. And then beta has negative 1, so 1, but in the negatives. And then, what is that? Gamma is 0. Okay. We also have to know something about, okay, those are going to attract something, right? They're going to attract this way, so that's the force. And as we know, any kind of force means there's an acceleration. And also, any kind of mass means that the acceleration has something to do with, you know, the mass. So alpha is really massive. It's 4u. Okay, this one is so tiny. It's so tiny. It's like u divided by 2,000. Okay, so it's really small. And then this one is 0. So 0, 0. Okay, so it's really easy. The gamma is super easy. It just goes straight through because it's not charged, so it's not attracted to the other side. Nothing happens to it. The beta is negative, so it's attracted to the positive side. It has a smaller curve because it's lighter. So that force acting on the attraction on it from the negative is going to pull it more. And then the alpha has a bigger radius because it takes more of that force to move that mass. Remember, the mass is way more massive than this. And so there you have it. Okay. The electrical force attracts negative to positive, and the negative side attracts the positivity of the alpha. But because the mass of the alpha is so big, it takes inertia, right? Its momentum as well also carries it further before its turns. It takes a lot more force to move that thing towards the side, to accelerate it towards that side. Explain the curvature path relative to momentum. Oh yeah, pretty much that's what I just did. I just did that. So the charges will be attracted to their opposites. Momentum of the alpha, even though it's much slower, its mass is so much more than the beta. Okay, the difference in velocities is only about 9x, but the difference in masses here is about, oh, I don't know, 8,000x. So it means that the attractive force, even though this is twice the attractive force of this, okay, so what? It might affect this by 18 times. Okay. The thing is, the mass of this one is so much smaller than this that it causes it to turn more and accelerate towards the sides more. All right. Okay. Circle the best response. The direction of the electron between is. I think you. Okay. So the problem with this exam, we don't really get into this until year 12. It has changed since 2016. The syllabus has changed. So if you really want to know, um, the electric field around any charge is always from positive to negative. Okay, so in that case, it's going to be down. See, positive to negative. So that's it. Yeah, that's it. Okay, does that help, Cuban? Don't worry, I've got this video. You can refer back to this part of it if you didn't get what I just said now. I did want to look at one more other one, guys, before we go today. I did say I was going to. I told myself I would go till 3 o'clock for you guys. Okay, so 21. So here is a nuclear fusion reaction. It's looks like a nitrogen and proton being combined and changing to an oxygen atom, and gamma is released. Okay. So use the data in the table below to calculate the energy in MeVs. Okay, released in the reactant in the reaction. So there's going to be some energy released. What we got is the reactants on this side. We got to find their mass. So we got to find the mass defect, which is going to be these two. 999,234 plus 1.00728. All that minus the side. There's no mass of that, so it's just going to be 14.998677. 677. Okay. Yeah. Why don't we find that? Two, three, four minus 1. Okay, so plus, oops, I'm looking at this. I didn't add that. I should have. Okay, so I got this. It's going to be -3, so 1, 2, 1, 2, 3, so it'll be 0.00787. You could just put that in the calculator. So there it is, the mass difference in atomic mass units. I believe that. There it is. So if we want MVs, the energy in MeVs, then what we take is that 0.007837 and multiply by the number of mega electron volts per atomic mass, which is 935, I think it is. Is it 935? Just double check. It's 931. See? So I'll take that amount and I'll just multiply it by 931 million EVs. So we get 7.30 MEVs. Get around it. Easy peasy. Easy peasy. Mass is converted to energy in nuclear reactions. In what form could this energy be? Describe the two examples. Well, heat energy, right? That's what we're doing. Heat energy in the form of vibrations of particles of the daughter. It could be, yeah, the kinetic energy, so the vibrations of heat, or the kinetic energy of the daughter, these ones. It could be the radiation in form of gamma. Okay. In the form of gamma. All right, last part, I think. C and D. All right. Oh, what is this? This is the binding energy per nucleon versus the mass number. All right. So what does that mean exactly? It means that in the nucleus, the binding energy, when you break it apart, is the energy that's going to be released when you break the atom apart. Okay. And this is the binding energy per nucleon. So it depends on how many protons and neutrons are inside the nucleus. And sometimes you ask questions like this. What happens is you find the mass defect and you find the difference in the mass, and that's the total energy. But that's just total energy. The binding energy per nucleon then takes it and divides by the mass of the atom, because that's really is the mass number is really the number of nucleons, right? So 235 is the number of protons and neutrons together. Okay, so we read this right. It means that for as you get bigger and bigger in mass, except for a lithium, the trend is that you end up with more energy per nucleon until this point here about iron. Then it starts to go downwards. Okay. So that's how we read the graph. So the smaller atoms, except for this little part here, release more energy per nucleon. It takes more energy to keep them together than these bigger ones. That's why these bigger ones are more unstable. What is for the number of them and the binding energy per them? That's all. What is the binding energy? Essentially I measure in the context of nuclear physics. Well, it basically is the energy required to, well, separate the nucleons in the nucleus. But you could also say by separating them, we could also release that energy. Okay? Or energy released when nucleons form a new nucleus. Yeah, because the combined nucleus is always less mass than the individual nucleons that comprise it. So where did that mass go? Right? And it went to, has to go somewhere. Okay. Any questions? Any other questions? We got the last one here. What does it say? Oxygen 16. Nucleus has a mass of this. Okay. Proton has a mass of this. Great. And a neutron has a mass of this. Calculate the average binding energy per nucleon for the above shows you to allows you to verify your answer. Okay. Well, let's see. The mass, the total mass, I should say, whoops, of nucleons equals, well, it's oxygen, right? So that means there are 8 protons plus 8 neutrons, because there's 16 total of them, right? Just we're looking at the nucleus, not we don't include um, electrons when we're talking about nucleus, because nucleons are just the ones in the nucleus. Okay, so that's 8 times 1.00728 plus 8 times 1.00867. Okay, so that should all work out to something. 8 times 1.00728 plus 8 times 867. Okay, so we got 16.1276. And you can see that it's more than the mass of the nucleus. So why? What happened to that mass? Well, it released in the form of energy. So why don't we find the difference in mass? It's this individual ones, 1276 minus 15.990526. Okay, and we're going to subtract that, the nucleus itself, and we can see there is U, that's the atomic mass, right? You can see that they showed us the units right there. And it says, again, the amount of, calculate the average bindings per nucleon in MU. Okay, so we're going to get this. We're going to find the total energy released here, which is going to be 127.6584 MeVs. Remember, you don't have to round in the middle of the question. We're still working on this. And that's the total energy, but the number of nucleons that there are, okay? So the mass has been converted to energy to bind these particles together. Divided by 16, because there are 16 of them per nucleon. What we end up is 7.98 MeVs per nucleon. Okay, guys? Done. Perfect timing, 2:58. Couldn't time it any better. Yes. Okay, so I'm going to post this video again if you want to review these questions. Good luck tomorrow, guys. Remember what to do. Yeah. These are the important things you got to do for tomorrow. So keep studying today. You know, take a little, like a longer break and then come back to it. If you have any further questions, do you have a particular question you want to ask, just shoot me an email like this guy did. I'm not going to name names. Just let me cross them out. Okay. So this student here asked me a question, but he sent the photo. See? He sent me a photo. You already gave yourself away, Kuman. Don't worry. Okay. I didn't give you away. Just like that. And I was able to, I said I would answer it today, but for you guys, I'll answer it in the email. Okay. All right, guys, that's it for today. Have a good one. Good luck tomorrow. Don't forget the tips. Bye.
Bye, Mr. Colleen.
Have a good night. Yep.